Hi there, welcome back. We're going to begin moving into operations with nth roots. So the first two that we're going to look at is how do I multiply nth roots together, and then we're going to look at how do I divide nth roots, and in particular how do I rationalize a denominator. We've done it with square roots, now we're going to do it with third, fourth, fifth roots. All right, the product property of radicals said you can multiply radicals as long as their index is the same. So notice that I have an n and an n here indicating that they're the same, so I can pull them under one single radical sign with one index. So for example, I can do the cubed root of 2 times the cubed root of 7 is equal to the cubed root of 2 times 7, which is 14. And then I would look to see if there were any perfect cubes that I could pull out, which in this case there are not. All right, so a couple things to think about is that if you have coefficients or factors that are already in the front, you're going to keep them out of the front, and they're going to get multiplied by anything that you move to the front. Anything moved to the front. Okay, so any perfect nth roots that you pull out, you're going to move those to the front, and then they'll get multiplied by any coefficient that is already there. All the factors that can't be moved, that remain under the radical, well, they're all going to be multiplied together. So let's take a peek. This is kind of a challenging one, but let's just kind of get an idea of where we're going. So I'm going to move everything under the single cube root, and so I get 3, and now I'm going to move my 9 there, and I'm going to write it as 3 squared, and then I have an x here and an x to the 4th there, so x to the 1 plus 4, just like our rules of exponents, y to the 1 plus 4, so I have 2, and then I have the cubed root of, now I'm going to combine 3 cubed x to the 5th, y to the 5th. Now I'm going to start my simplifying. So I get 2, and then I have 3 to the 3 over 3, x to the 5 over 3, and y to the 5 over 3. Right? So this is an even divide, so it's going to come out as a 3. 2 times 3. This is not, the x is not an even divide. 5 divided by 3, I can get one full group of 3 out. That's an x, but I'm going to have 2 of them that are going to stay underneath the cubed root symbol. So that's an x squared. Y to the 5 divided by 3, I can pull out one full group of 3 y's, and then 2 of them are going to stay under. So you would just multiply 2 times 3 xy, so you would get 6xy cubed root x squared y squared. All right, I just don't have room to write that. 6xy cubed root x squared y squared. Just like that. That would be your final answer. A couple things to think about. Indices have to be the same. Move all factors under one radical sign. Simplify by looking for perfect nth roots. Multiply factors in the front. Multiply factors under the radical. So let's try it here with this number 1. And I have a 5 and a 3 I'm moving to the front. And then I have a 10 squared, and then a 10 to the 1st, and an a cubed, and an a. So I'm going to just do some cleaning up. I'm going to make that a 15 out there. I can do that at any point. And this is 10 cubed, a to the 4th. Now I'm going to apply my power over index. So I'm going to get 15. This becomes 10 to the 3 over 2, a to the 4 over 2. So I can pull out one group of a pair of 10s. So this is going to be 15 times 10, and then I'm going to have still a single 10 underneath the radical. This is an even divide, so I just pull out an a squared. So I get 150 a squared root 10. All right, let's try another one. I'm going to move the 6 and the 4 together. You can multiply them together at any point. And then I'm going to pull everything under the radical. This is 2 cubed. All right, I just do prime factoring on that. And I get 2 to the 3 plus 1. And then I have c cubed and a c. That's going to be c to the 3 plus 1. And then I have d to the 5th and d cubed. So that's d to the 5 plus 3. Those are just our rules of exponents. Okay, that's a 3. All right, I'm going to move over here, give myself a little bit more space. I'm going to take that to 24, multiply that out. I can do that at any point. If you don't want to do it yet, you don't have to. And then this is the cubed root of 2 to the 4th, c to the 4th, d to the 8th. And now I'm going to apply my power over index rule. And this is going to be 24 times 2 to the 4 over 3, c to the 4 over 3, d to the 8 over 3. And I'm going to simplify. This is going to give me one group of 3 2's, so that's 2, and that's going to leave me the cube root of 2 underneath. Same with the c. I can pull out one group of 3, and then that's going to leave me with a remainder of 1, so I have a c underneath the third root. And then the d, 8 divided by 3 is 2, so I'm going to pull out 2 d's, or d squared, and then I'm going to have 2 d's left over, or d squared left over. So I'm going to get 48c d squared cube root, that's a times, 2c d squared. Okay? Why don't you try this one as your video question and then come back and see how you did. All right, this is a 4th root, so I'm going to have 2 times 3. I've just moved those to the front of everything, and I'm going to combine under 1 4th root. This is 2 cubed, so I have 2 to the 3 plus 1. My other one came from this 2 right here. X to the 3 plus 5, y to the 2 plus 2. I'm going to go ahead and multiply those together. That gives me 6, and I have the 4th root of 2 to the 4th, x to the 8th, y to the 4th. All right. So now I'm going to start pulling out my perfect 4th roots. This 4 and this 4 are going to undo each other, so I'm going to have 6 times 2. Okay? And then I'm going to have x to the 8 divided by 4. Well, that's going to be x squared. And then I'm going to have y to the 4 divided by 4. So think about your even, even, odd rule. Even, even, odd. So this is going to be 12 x squared absolute value y. Okay? And if you need to see this one is 2 to the 4 over 4, that's fine too. All right, the quotient property of radicals basically says the same thing. Same index. Need to have the same index. And we can pull them under one radical sign as a fraction. Maybe we can reduce and make our life easier, all right? Or you might result in a perfect nth root or something, like in this case, if I take the cube root of 54 divided by the cube root of 2, if I pull them under the same radical, this reduces to 27. And we know that the cube root of 27, well, that's a perfect cube. So because it can be written like this, and those undo each other, and so we get a 3. So not every radical can be simplified like that, so it's really important that we know how to rationalize the denominator. So we're going to talk about that for just a little second. So what we're doing is we're looking for whatever we need to do to make the denominator a perfect nth root. We've done it with square roots before. So if I want to make this a perfect square on the denominator, I'm going to multiply by its identical thing, because then it'll become a perfect square. Whatever I multiply the denominator by, I have to multiply the numerator by. Oh. And so I get the square root of 15 over the square root of 9. You could also think of this as the square root of 3 squared. And that's going to simplify to the square root of 15 over 3. Now, when you have higher roots, the easiest way to approach this is to ask yourself, what do I have to multiply my denominator by to make it a perfect nth root? So in the case of example 2, we need it to be a perfect cube root. Perfect cube root. All right, so a lot of times what I'll do is I will prime factor my coefficient, and I will write this as the cube root of 5 squared t squared. Okay, so remember, I need my power under my radical sign to match my index. So what do I need to multiply my denominator by? Well, I need the cube root of 5 to the first, t to the first. Whatever I do to the denominator, I must do to the numerator. So I'm going to get the cubed root of 2 times 5 is 10. Tx, I just put them in alphabetical. And then this becomes the cubed root of 5 cubed t cubed. Now both of these are perfect cubes. So I'm going to get the cube root of 10tx over 5t, and I'm done. Now sometimes if you notice that your coefficients are multiples of each other or even divides, it's helpful to bring them under the same radical. So I can rewrite this one as the cube root of 3x squared over 27x to the fourth. Now I can reduce underneath my radical sign, and I get the cube root of 1 over 9x squared. 3 goes into 27, it cancels, and I get a 1 and a 9, and then my x squared divided by x to the fourth leaves me an x squared on the denominator. So now I'm going to split it back up again, and I get the cubed root of 1, and that's just 1. And then I have the cube root of, and watch how I write this. This helps me see what I need. Prime factor this 9 is 3 squared. And then I have an x squared. So remember, to make a perfect nth root, I have to get my power under my radical to match my index. So I'm going to multiply both top and bottom by the cube root of 3x. I do that because it makes my denominator a perfect cube. So I'm going to get the cube root of 3x over, this becomes the cube root of 3 cubed, 3, the cube root of x cubed, x, and there it is. That's rationalizing, all right? So sometimes we don't have to rationalize, sometimes we do. I'm going to do number 1. I want you guys to do number 2 on your video question. I see that 50 is divided by 2, so I'm going to bring it under the same radical sign. And then I'm going to actually divide. And I know that the square root of 25 is 5. I don't need to put plus or minus because it's asking me for the principal root. You try number 2. All right? This I'm going to split up, and it becomes the square root of 25 over the square root of 7, which is 5 over the square root of 7. Now I'm going to rationalize my denominator, and I'm going to take 5 square root of 7, and I'm going to multiply top and bottom by the square root of 7. And this is 5 root 7. And whenever I multiply the same square root together, I just get what's ever underneath here. You can think of this as the square root of 7 squared. They undo each other, so I get a 7. And here's your final answer. All right, I'm going to do number 3. I'm going to let you do number 4. Number 3, I don't have anything in common. Variables, nothing. So I'm going to split it up. And I get, this is nice, I get 3 cube root of x to the 9th over the cube root of y to the 5th. This is an even divide, so I get x cubed. And then this is y to the 5 over 3. So I have to simplify this. All right, I have x cubed up here. I can take out one group of 3 y's. So I get y, and then I get the cubed root of y squared. Okay? So I need to get rid of this cube root of y squared. So that means I have to multiply top and bottom by something that's going to make this a perfect cube. Well, that's going to be the cube root of y. Cube root of y. Right? So my numerator becomes x cubed times the cube root of y over, I have this y, and then these two become the cube root of y cubed. Well, that's nothing more than y, so I have y times y in my denominator. So I get x cubed, and then the cube root of y over y squared. You try number 4. All right, this is already broken up. There's nothing in common, so I'm not going to try and pull it together. I have the 4th root of 3 over the 4th root of 2 squared z. Now, I have to get my powers under my radical sign to match my index. So I need to multiply this denominator by the 4th root of, I need 2 squared, and then I need a z cubed. Whatever I do to the bottom, I must do to the top. So I need a 2 squared and a z cubed. Now I'm going to multiply these together, and I get 4. The 4th root of 3 times 4 times z cubed. Over the 4th root of 2 to the 4th, z to the 4th. All right, this is 2 to the 2 plus 2. That gives me 2 to the 4th. And this is z to the 1st plus z cubed, or z to the 1 plus 3. All right? And now I'm going to simplify, and I get the 4th root of 12z cubed over 2z, because these go out and these go out. And that's your final answer. Last pairing, I'm going to do number 5, and I'm going to let you do number 6. So I can reduce this under one radical, so I'm going to do that, and I get 3y cubed over 2. This y cubed is going to come out as a y, and then I have the cube root of 3 over the cube root of 2. All right? And now I'm going to multiply top and bottom by the cube root of 2 squared. The cube root of 2 squared. And so I get y times the cube root of 3 times 4 over the cube root of 2 cubed. So I get y times the cube root of 12 over 2. Okay, number 6, you try this and then come back. All right, I'm going to keep this under the same because I noticed that 243 is 3 to the 5th, and then I have k cubed, and then I know that 9 is 3 squared, k to the 6th. All right, so now I'm going to simplify, and I get 3, the fourth root of 3 cubed over k cubed. Now I'm going to separate them. Right now they're all under one radical, and now I'm going to separate them. I have the fourth root of 3 cubed over the fourth root of k cubed. I need to make this a perfect fourth root, so I'm going to multiply top and bottom by the fourth root of k and the fourth root of k. So my numerator becomes, now these are the same index, so now I can multiply them together, and I get the fourth root of 27k over the fourth root of k to the 4th. Well, these undo each other, so I get the fourth root of 27k over k. It's 4 divided by 4, so it's an even. I get an odd, so look there, I'm going to put in absolute value bars. All right, how do I know when I'm simplified? All the perfect nth roots are gone. All the fractions have been removed from under the radical sign. There are no radicals in the denominator. This is our daily assignment. Thanks for listening.